All right, guys, good. Welcome. Let's take a moment to look at probability in general for a bit, but also primarily a type of probability called experimental probability. When we talk about probability, we're basically thinking about a situation that has uncertain outcomes, right? If I roll a die, for instance, maybe I get a 1, maybe I get a 2, maybe I get a 3. I'm not exactly certain about which outcome I'm going to get, but I'm able to analyze the situation still, and that's the idea of probability. Just like when we talk about the likelihood of a certain number on a dice or the likelihood of rain today or something like that, we could express this as a percentage, like there's a 50% chance of rain today or a 50% chance of tails if I'm flipping a coin or something like that. And we should be aware, oops, this is really thick. That's really thick. We should be aware that we could talk about the percentage. We could also talk about the percentage as a decimal as well. So there's a little bit of that involved with us. We're talking about 50% for a probability. We could also say zero point 0.5 because those are equivalent statements, right? Or equivalent numbers. We could also say all the way up here at 1 for certainty would mean 100% likely. If it's 100% likely that it's going to rain today, then it's certain that it's going to rain. All right? That's the number also equivalent in value to 1. All the way down here on the other end of the spectrum, let's say it's absolutely impossible for, you know, today to be in July because it's not, right? If that's an impossible likelihood, of course, 0% also has the value 0. So this spectrum is basically communicating some possibilities of probability to us, for all the way from impossible up to certain. Maybe if there's an equal chance from one or the other, 50%, unlikely or likely, right? This is how we can express it as percentages. But ratios too, and we'll talk a little bit about that too when we see some examples. Probability could be something that we can analyze based on an experiment we do, right, which is based on results we get and seeing how many, like we tally up a frequency like we did by rolling the dice the other day. Or you could just imagine the possible outcomes, and this would be an example of using theoretical probability. We'll talk more about that a little bit later. Okay, so to talk just a bit about probability, generally speaking, take about 5 minutes to watch this YouTube clip about how we can see it in the world around us, and then just take a moment to pause and in your notebook reflect about these questions. When are we seeing probability, generally speaking? When are we using it, right, as a tool, as a mathematical tool? And then also name when it can be useful for us, right, a time when you might want to use it as a tool to help analyze a situation. So you can pause this video now and see the YouTube one to reflect a little bit on this question. Thank you. As we continue, we can go into some terminology that will be useful when we talk about probability. One term that comes up is the term trial. Right? The word trial here is telling us basically one particular moment that we get when we're running an experiment, right? When we're doing an experiment like rolling the dice 100 times, right? One trial would be one roll. The number of trials we did in our dice experiment was 100 because we rolled the dice 100 times. One particular trial means one of those rolls. The particular outcome was what you saw when you rolled that dice. So an outcome for that six-sided die could be a 1 or a 2 or a 3, all the way up to a 6. Say 1 or 2 or 3. Those are the possibilities in the case of a dice for the outcomes when you roll it. Frequency, like we saw, remember from the last unit, we talked about frequency tables, right, and frequency histograms. Frequency is counting a number of numbers, right? If I'm looking, for instance, at the list 1, 1, 2, 3, remember we're talking about mean, median, mode. If we're thinking of the frequency of the number 1, we would say the frequency here is 2 because I see two 1s. And there's only 1, 2, and there's 1, 3. If these were the rolls that I got, the frequency, again, of the 1 would be 2, and then the frequency of the 2 would be 1, and 3 would be 1. The relative frequency means I need to relate the frequency to a total number of trials. This is what you did probably at the end of the experiment from yesterday. If I saw that I rolled the 6 20 times in my experiment, but there's 100 rolls total, then in that case I could create this ratio where the frequency was on the top. Let me rewrite this. The frequency was on the top and the total trials was on the bottom, right? Those two numbers are important to compare in order to get a relative frequency, or generally speaking, what we mean is put the frequency we saw for this outcome, like the outcome 1 or whatever, compared to the entire experiment we did, compared to the total trials that we did. If I happen to see 21s for my 6-sided die for 100 trials, in this case, this ratio could also be simplified to a fifth, because divide the top and the bottom by 20. You could also write this number as 20%, of course, because 20 divided by 100 would be 0.2. You could also write that value, 0.2, and my calculator would be what I would see if I type 20 divided by 100 or 1 divided by 5. And that's the same thing as 20%. Remember, moving the decimal 2 spots over for the percentage. So if I'm thinking about relative frequency, I'm thinking about a ratio, because I'm putting the frequency of something I'm looking at in context with the total number of trials that I ran, and that means I'm looking at a ratio comparing top and the bottom. That fraction can be divided out to a decimal or to a percentage, and as a result, those are two different ways that we can express probability, as a percentage or as a ratio. Last idea here with the topic here is the experimental probability. This relative probability, or this relative frequency rather, that we're talking about is the same thing as what we would refer to as experimental probability. The reason why is that we're running an experiment like we did with the dice to collect data that then we're using to create our ratio. Data like how many times did you see one of those outcomes and how many total trials did you conduct in that experiment. Right? Let's go to an example so we can see how these terms are being used in context. Let's say we spend our Saturday tossing an ice cream cone empty up into the air 300 times, right? This would be one way to collect data about how often certain outcomes are occurring. I'm not certain if this cone is going to land on its side or if it's going to land on its base when I toss it up in the air, but I do know those are two different possibilities, right? And as a result, I could say those are two outcomes whenever I do one trial of my experiment with 300 different trials. I'm going to toss it up and see what happens, and those are the two possibilities, so those are the two outcomes. So one thing we could say when we see this situation tossing it up 300 times, we see after I do it, okay, here's data that's given to us. It's landing on its side 203 times, we notice, on its base 97 times. Right? So the idea here, how can we talk about the things that we know? The number of trials is 300. It's 300 trials because we did this thing to see what the event was 300 times. The possible outcomes in this case are only two possibilities, like it's either going to be sides or it's going to be the base for this cone. Can you think of another time when we only see two possible outcomes? There's no dice that only has two sides, but coins have two sides. If we flip a coin, that's very common for probability. In that case, that would be either heads or tails, also a case where there's two outcomes. Let's think about frequency. The frequency of, based on this experiment, the frequency of the side outcome was 203, right? The frequency of the other outcome in this experiment, the base, is 97. And these are all important numbers to notice for us because these numbers are going to appear in the ratios that we get when we work with, in this case, experimental probability. If we wanted experimental probability, remember, that means I'm just putting the frequency we found for these outcomes in context with the total number of trials that we ran. So in this case, the relative frequency, I'm going to abbreviate FREQ, the relative frequency of this outcome side, the side of the cone, is this frequency 203, but again, compared to the total number of trials, or put into context here, how many times did we flip that cone? I mean, if I flipped that cone 10,000 times and I only found 203 for the side, that's a very small ratio, isn't it? Right? But if I ran only 203 trials and every single time it's landing on its side, well, I could predict that the next time I flip it, it's going to land on its side again because I see it every single time. In this case, it's 203 out of a total of 300 total trials. If you type that ratio into your calculator, divide it out, you'll see it's approximately equal to, means we're just going to round it off and not give the full thing. It's about 0.677. And if I change this to a percentage, that would be 67 or 68%. We'll say 67.7%. And that's an interesting number for us, right? That means most of the time, because this percentage is above 50, right? Most of the time we're seeing this cone land on its side. The last idea here would be to think of the relative frequency of the other outcome, which would be the base, landing on its base. Again, this is how many we saw for the base divided by how many we ran for the entire experiment. So remember, we saw this base in this experiment 97 times, but it was out of 300 total trials. Looks like this should be less than half. If you type that in your calculator, you should see 0.323, and that's going to also be the same as 32.3%. Okay. So remember, as we kind of wrap up this idea, these relative frequencies, they're both also what we could use to answer experimental probability, questions of experimental. If I ask for what is the experimental probability of getting the side, we're taking that ratio. It's what we would say as the experimental probability of the side. It's the same thing to talk about relative frequency. They're identical in this case. All right, so it's important to notice here, this is basically this understanding about how we can take the data we get in an experiment. That's a tool we're using that we could use to make a prediction, right? If I flip this cone again for 101st time, right, there's a 67% chance, based on the data we already have, that we're going to see it on its side for the outcome. And there's a 32.3% chance that we would see it on its base. So if I flipped it 100 more times, we could say, yeah, most of the time we would predict to see it on its side, but in less than half the time we would see it on its base. You should be aware also that these numbers are going to change the more trials you do. If I continued the experiment and I flipped it 200 more times and it was 500 total, my new experimental probabilities, or my new relative frequencies for these outcomes, would have a 500 in the bottom, right? Because that would be the total number of trials I'm comparing it to. Generally speaking, the more data you get, the more reliable your probabilities are, right? The more, you could say, accurate they're becoming, because when you're getting more and more data, right, you're what are you doing? You're gathering more data. You're understanding the nature of this object, tossing it up in the air in with a more robust way, right? Because you're taking it more and more times. So that's the idea here for this first section on experimental probability. Be sure you see in your notes this example and to apply these numbers, and you're being sure also to notice these terms that are coming up, because when they're asked in the future, you'll be able to refer back to your notes to see what that looks like. If you have any questions or concerns, please do let me know, and thank you for watching.